in general, okay, now I get the book. The Wikipedia page here. Okay, so in general, how do you decide which basis to transform on? In general, if you have a mathematical problem. So it depends very much on what do you want out of this expansion. If it's a featureless structure, meaning momentum is conserved, Fourier transform is usually the easiest and the most convenient thing to use. If let's say if you take optics, if you're just propagating in free space or along an optical fiber, the easiest is to do a Fourier transform in order to understand the properties of the wave propagation.
Because it's like a free particle.
Right. If you are describing a system with gain, I'm not so sure that that's a good language to use. Depends. Okay, here you can say we're fortunate enough, or we had enough of insight to see that this system with a Gaussian initial condition would be the easiest to handle mathematically. Okay, so perhaps it's long and ugly, but we found Bn. Now, if I want to see how the system behaves as function of time, I have to go and perform the summation. So I'll keep here only the end result. Basically replace this with what we have written here. And just copying it. Comes from this term, it doesn't depend on n. The plus half doesn't depend on n. Okay, looks quite ugly. But I have here a couple of things I can do to make it a bit simpler. Note that all this are constants. Depends on t, but doesn't depend on y or on n. Okay, just in the power of n, it's e to the I omega nt. Looks quite innocent, but actually here we solve the summation. Why? Because up to constants outside, this is exactly the expansion of Gaussian. And we can write it down as y0 t. Should be here a minus. So I start to see the physics here. Why? I have some normalization factor, and the behavior that's more, which is Gaussian, meaning that the wave packet, in some sense, and I'll explain in a moment why I say in some sense, remains Gaussian, but its center moves with time. How does it move in time? Like e to the power minus I omega t, which is a classical solution, oscillator which depends on time. Now, it captures some of the truth, but not all the truth. Why? First of all, this is a description of a wave function, right? And not of the probability of finding this particle. Now, it's not immediate to translate it for the simple reason. y0t, I'm trying to convince you that it's a position, right? but it has an imaginary part. A position can't have an imaginary part. So what I really should calculate here is the probability of finding particle, which is and then we'll follow how it behaves as function of time.
But how do you know that A0 is moving with time, or the
A0 is a normalization at the end of the day, right?
yeah, but the normalization are constant.
Not necessarily. If the wave packet breathes, I said that the center moves as a harmonic oscillator, a classical harmonic oscillator.
How did you get that? Like, where?
It's a guess at the moment because I see here a Gaussian around y0t. And y0t, did I erase it? Yep. Oh, no, it's here.
Yeah, but how did you get the y0t is equal to this?
I just looked. Look at the previous expansion, right? We had here just y0, all other up to some this constant outside was the same, right? So I pack it back into a Gaussian. The only thing that changed is that in the expansion, instead of y0 here, a few lines ago, I have now y0 times e to the power minus I omega t. Meaning that I can write it down simply if I'm taking this definition. Now, my point was, mathematically it's completely exact. Physically I have to be a bit careful, because if I'm just saying the center of the Gaussian is moving to a different y0, should stop me and say, but y0, the way that you have written it, has an imaginary part. And what do you mean that the center moves in an imaginary position? Has no meaning. Okay? So I'm telling you, okay, I don't worry, because that's a wave function. Wave function is not a physical observable. Physical observable is this fellow, psi squared. So now I have to take this wave function and understand what does it mean. How does the probability develop with time? Okay, I haven't done it yet. Now I'm going to do it. Okay, so just wrote down the definition of squaring. And I have to be careful because this guy has an imaginary part. So I'll look a bit more closely on what do these terms mean. So I have here the index of the exponential, half. Just wrote it down. The power of the exponential. Okay, first term.
Well, yeah.
Nothing beyond the trivial trigonometry. Just open cosine to omega t. Again, elementary trigonometry. And finally, I'll rewrite it as okay, so just writing down the result of the experiment and what's written here. So the Gaussian with a center around the classical position remains, but there is some normalization that is t-dependent. Not extremely surprising. But the Gaussian form, the important thing is that the Gaussian form remains. And someone should have thrown stones at me because this is a minus. It can't be. This problem comes from here. Okay, so our basic intuition worked, but we should have been a bit more careful with identifying the behavior because it's a Gaussian, but in some sense a breathing Gaussian.
We need to have a minus there too, right?
Yeah. Okay, so we have shown an example with working with a wave packet in an harmonic oscillator, which we have used all the equipment of Hermitian polynomials that we learned during the solution of the Hamiltonian. In general, this is a behavior that returns again and again when solving the behavior, the time-dependent behavior of any potential, because all the mathematics that we put into calculating the eigenvectors of the Hamiltonian, the energy eigenvectors, will come back to be useful in the calculation of the time dependence, because we always have to span the initial wave function in the basis of the solutions of the Hamiltonian. In this case, it gave us a rather nice physical behavior. Okay. Fortunately, we're leaving now 1 dimensions and moving to 3 dimensions. Well, unfortunately, because life usually at higher dimensions becomes more complicated. Okay, you can stop me here and say, well, why are you starting with potential? What's the behavior of a free particle in 3 dimensions? What is the wave function? What are the eigen values?
Can you just say it would be a wave packet of all?
Leave wave packet. I'm asking what are the eigenfunctions, energy eigenfunctions, or the solution of the Hamiltonian of a free particle in 3 dimensions. So the easiest case of 3D potentials is no potentials. Right? But truth be said, we have solved it already. What do we know? From 1D, we know that the eigenvectors are the Dirac normalization. Right? So the eigenvectors are these things, eigenvalues and kx, if I have no periodic boundary condition, just any value. If I have periodics of those are the 2 pi times n over L, and then I have to correct the normalization to a Kronecker behavior, not the ideal. Okay. Okay. So this is the potential, to a minus here. px squared plus py squared plus pz squared. Right? Then I can do separation of variables. Life's very easy. And psi is phi. This way. Okay. Because the scalar multiplication here is kx times x plus ky times y plus kz times z, which is written there. Okay, so we're expert at free particles in 3 dimension. Actually, we are already experts in free particles in any dimension. It might be interesting to stop a moment and ask ourselves, just, this is in Cartesian representation, x, y, and z. What will happen if we go to spherical representation, theta, phi, and r? I'll define everything exactly in a couple of moments, but let's look what we have here, basically. We have here some vector which is a k direction, right? And some vector which is the r direction, right? To make life easier, I could put the z direction in the direction of k. It's my prerogative to choose a direction, right? So then I'll be left just with where theta is just the angle between k and r. R is the second coordinate, and it doesn't depend on phi. Right, so this is a representation of this wave function in spherical coordinates. we'll see that sometimes this behavior is easier, sometimes this representation of behavior is better. Yeah.
Let's say if it's not spinning, right?
What do you mean spin?
Like rotate.
A free particle doesn't rotate, right? If you are asking about the spin degree of freedom, spin up and spin down from the beginning of the course, we'll get there. But at the moment there's no spin, no magnetic moment. The electron is a free particle. Okay, if someone can get where is a plane wave description and when is the spherical description better?
When you have a potential depends on R.
Right, one thing is if I have a symmetric potential
On R.
which depends only on R, not on theta and phi, and if I'm describing a scattering problem. Because then I have some wave coming in, but the scattered wave will come out in all directions, right, from a center point. So then this description is convenient. Again, we'll run into it in details further.
Like he came on one dimension, like on.
Look, how do you do usually any elementary particle experiment? You take some particle, you accelerate it to some velocity, and it's usually described by a plane wave, because it comes in one direction, then it hits something. What happens? The outgoing probability is already spherical, because it comes up. Perhaps it's skewed, so more probability of coming in a certain direction than in another direction.
Like when you throw glass on a wall and then it's getting
Well, the easiest description is if you look on a wave in a pond that has a rock. Right? So it begins like a wavefront, gets to the rock, and then you see rings around the rock. That's a description. So for the ring part, this is a much more convenient description. For the wave front, this is much easier. As usual, depends. So we are expert at no potentials. What is the energy? Okay, no problem. I'll just write it down once because for some reason students have a tendency to mix up stuff here. Remember, here the energy is of vector k, and it's vector k squared. Vector k squared is kx squared plus ky squared plus kz squared. Not any other forms that you can think about. Okay, so we're already experts in no potential. So we are looking at spherical symmetric potentials. What does it mean? This is a general potential, depends on vector R. And we are considering only this case, where it depends on the magnitude of R, not on the angles. Which most physical potentials, the best example is just the electrostatic potential, depends on the distance, not on the angle. If I would like to describe the behavior of the electron around the dipole, then life will be more complicated. We are considering spherical symmetric potential. It's not surprising, but in this case, instead of working with X, Y, and Z, we would like to work with R, theta, and phi. So just now giving you textbook definitions of transforming from X, Y, and Z to R, theta, and phi, including the derivatives, which you probably have already heard at some point. Okay, what does it mean? Okay. Assume that I have a vector R. Okay, so R is still the distance R. Theta is the angle between this guy and this guy. And phi is the angle on the xy plane. That's why we have here only xy. Is there anything special about choosing z? The answer is no. We have here a spherical symmetric behavior and it doesn't matter. Sometimes it will turn out to be more convenient to put z in some specific direction. As we saw, let's say if we have some k, it's easier to put z on k.
Yeah. shouldn't phi be the other side if you do x over y?
So over y, so yes. So I defined it as x over y. Yes. Thank you. Okay, so while x, y, and z could receive any value between minus infinity and infinity, here R has values between 0 and infinity. The shortest distance is 0, or positive number. Phi can be anywhere between 0 and 2 pi. The theta could be only between 0 and pi. Okay, just for completeness. Okay. As I said, we're just repeating things that you should have encountered somewhere on your study. This is the unit vector, therefore we don't have a distance r here, because it's a distance 1. And the most crucial terms we will need here is our divergence of a function. Now it depends on r, theta, and phi. Fortunately, for a symmetric potential, we see that the force doesn't depend on phi, doesn't depend on theta, and therefore it will be only either towards or away from the central point. Hopefully I didn't make here some mistake in the plus minus definition, but as I said, any textbook will give you. Definition for me, the most important point is this realization. Force is the derivative of the potential. The potential in this case depends only on r, so the force will be either outside or towards the charge or whatever. Yeah.
But now the velocity is dependent on.
I didn't say that life is simple. I'm just telling you that if the potential is symmetric, the force is always towards the center or out of the center, as you know from gravity. Okay. And last and most important, why is this so important? Because this in the Schrödinger equation will be the kinetic term. And F will be the wave function. Definition. And basically, our task now is to solve equations of the form or in full glory. Okay, now you understand why no one gave you the solution of the Schrödinger equation in modern physics. It looks scary, but we know that it can't be so scary. Why? Because we solved this thing up to moment. Up to losing this term, we know the solution. E to the power I k r cosinus theta divided by the normalization. So, and this includes all these scary terms, right? So it's scary but doable. And that's exactly what we're going to do during the next 2 lectures, more or less. And actually, the main point that we will do is separate it to 2 different problems. Already at this stage of life, you're used to the fact that we have a complicated equation with multiple variables. We try to do separation of variables. So the first separation that we are going to do okay. We separate the angular dependence from the R dependence. And the angular dependence will turn out to be very interesting and very important for the simple reason that basically whatever the potential is, this behavior is built in. From a physical point of view, it's the conservation of angular momentum. Because if the force always works towards the center, angular momentum is conserved. So, at the point that we will be able to solve this part of the wave function, we have a lot of knowledge. We can't solve yet the hydrogen atom. For that, we need to know the specific dependence of V of R, and that will determine this part. But this is common for all spherical symmetric potentials. We can already guess that it will have something to do with conservation of angular momentum. And basically, we'll see a whole mathematical operations that we'll develop in order to solve the angular momentum. In some sense, very similar to the ones that we developed for the harmonic oscillator. We'll have their creation and annihilation with different rules a bit, but the same basic idea. And that will give us a general solution on the angular momentum, and then we'll head back into solving the particular value of the R dependence of the wave function for a hydrogen atom. Okay, I think it's a good point to stop. And whoever this looks, can't use the usual term of like Chinese to you. Forever who it's not familiar with this, open Arfken or Boaz and refresh your memory. We'll read. Okay, let's stop here. And Chanukah Sameach.
Chanukah Sameach.
הפתרון של החלק הזוויתי, אז למדנו במפוס 3 הזה כאילו הרמוניות ספריות, שאתה אומר שזה שימור בין הזוויתי.
אתה תבין את זה.
זה ייצוג אחר או שזה אותו דבר פשוט כאילו?
פולינומי הרמית ואופרטורי הריסה ויצירה. לא הגדרנו מה זה תן הזוויתים, נכון? נגדיר את זה, נראה איך זה קשור